Today is a great opportunity. You are going to learn everything about how big stars form in the universe. I don't know, but let's start. James, could you please introduce yourself and what do you do for business?
My name is James Chibueze. Chibueze is my last name. I'm Nigerian and I teach at Northwest University and carry out research on Highmass star formation at the Center for Space Research in Northwest University. So
And
I would be, okay,
yeah, yes, James, go ahead.
I would be taking some time to explain in simple terms how big stars, which astronomers like me refer to as massive stars, form in the Milky Way. Of course, the principle would still apply for other galaxies apart from our own galaxy, which we call the Milky Way. So I will start from the smallest things, the smallest, well, I'll go from general to very specific. Um, when I mean general, I would try to paint the big picture and then I break it down till we get down to the smallest picture or the smallest scale. So what we are actually doing, things I'll be explaining today is what you can describe as multi-wavelength understanding or study of massive stars. By
Okay.
multiple wavelengths, you are looking at different processes or different emission processes that you pick up. Okay, so before I go into those details, I would have to highlight to you that I am a radio astronomer.
Oh,
So
yeah.
radio astronomy entails that I do not look at things, well, not that I don't completely, but my focus is on things that emit at radio wavelengths.
Okay.
So we do understand that we have what we call the electromagnetic spectrum, right? Which gives you from the longest wavelengths in the spectrum to the shortest wavelengths. The longest wavelength is the radio wavelength, which goes into meters and kilometers, okay? And one wavelength is the distance light will travel when a transverse light will travel when it makes a complete cycle, okay? So you go up one loop and then down a second loop, this length becomes your wavelength. So this can be very long. It can be meters. It can be centimeters for radio wavelength. It can also be very short. The optical astronomers use a unit we call Armstrongs or nanometers sometimes.
Okay.
Okay, so this is extremely short for the optical, but it can also be even shorter if you go to X-rays, which is high energy, right? So you have very short wavelength. So what I'll be describing to you, well, X-rays, gamma rays, those are all short wavelengths. What I'll be describing to you will be mostly things we look at in the radio. I will include some of the things I will mention information we gather from infrared. For the optical, for stars to already be producing optical light, the star is already born.
Okay.
So it's already a young age or middle age star. So I would not focus too much on massive stars that are already giving out optical. Okay,
Okay.
good,
Yeah.
awesome.
So
So I'll start from the,
basically, James, you are studying the stars and these bodies through their emissions and their radiations.
yes.
Okay, great.
So I pick up radio emissions from environments where these stars are forming. I analyze the kinematics, the motion of the gas, and the dynamics in the environment, and I use it to propose what is happening that leads to the formation of the stars.
Okay.
Very good. Okay, so now I start from the big picture. The biggest thing about the formation of stars is that they are made from gas and dust.
Mhm.
Now, just like humans, stars are born and stars die. Our star, the sun, is a very small star. It's usually referred to as a one solar mass. A solar mass is just the mass of the sun, which is about 10 to the power 30 kilograms.
Mhm.
So that is a very small star. The stars I will be telling you about how they form are much bigger than this star. They are usually 8 times the mass of the sun, which is 8 times 10 to the power 30 kilograms or above. It could be 10 times the mass of the sun. We have seen stars that are 100 times the mass of the sun forming. This is really massive. These are very big stars. And we think it's very important for us to understand how these stars form. The reason is because the structure of our galaxy, the morphology of our galaxy is strongly influenced by these big stars. Also, heavy elements come from these very big stars. So they are actually sources of heavy elements within the Milky Way. So their strong influence in the galaxy is one reason we need to understand it. We have a fair idea of how the smaller stars like the sun form. We know they also form in molecular clouds. Molecular clouds is just a huge cloud, just like the cloud you see in the skies, but a cloud of gas and dust. And we know that through gravitational collapse, this cloud will, because there is density, non-uniformity in the densities, right? So you will have a collapse in the gas and you form a huge core. The core will gain some angular momentum, rotating and accreting more material. Think about it, when you put in a colloid, if you put some kind of powder in water and you spin the material containing this mixture round, you will gradually settle all the particles to the ground.
Okay.
Good. So if you have a small core that is spinning around, it helps material fall into the central object and the forming star will grow in mass.
Mm-hmm.
Now, if you spin things around, you generate what we call angular momentum or angular energy. Imagine you have to tie a stone to a string and spin it, holding it strong. You will generate so much energy in that if you spin it forever, the string, no matter how strong, will break off.
Okay.
Because the angular energy you generated wants a way to go out of the system, because the system cannot sustain getting in much more energy from the rotation. Stars are rotating and accreting. They also want a way to carry out this angular momentum out of the system. So they do what we call ejection or outflow. So what happens is they accrete mass into their central core, but at the same time, they eject matter from inside them.
Mm-hmm.
So the rate at which they accrete is higher than the rate at which they eject. Therefore, the difference will be the growth rates of the star.
Okay.
Now, so when they eject materials, what they do is that they eject materials. Imagine this is a sphere, okay? It will eject materials uniformly around the sphere, but you have the rotating disk in this plane. Therefore, this plane is much thicker, okay? And therefore, material will tend to go out through the poles. That is one argument. The second argument is, if you remember, the sun and the earth have magnetic field in the poles, right? That is the reason we see aurora. Stars, including the sun, also have these magnetic poles. And the forming stars, we have seen that they have magnetic field that could help direct this outflow going out through the poles. And the outflows, we have confirmed from research, actually don't just go straight out, they rotate outward, carrying out away some of the angular momentum, therefore keeping the growing star stable.
Okay.
Okay,
Okay.
good. So we do understand this, most of this part in star formation generally, and we understand most parts of low mass stars, because we know the low mass case, they will keep accreting material until the density in the center is so high that accreted hydrogen will start combining with itself in a nuclear reaction, release a lot of energy, and form helium. That
Okay.
is what we call hydrogen burning. That is what part of the energy it releases is converted to the light we see. At that time, the star is born. Now,
Okay.
imagine that you light a fire.
Okay. Excuse me, James. So
Yeah, go ahead.
yeah, you say that the material keeps accreting inside the star until like a kind of reaction starts or is ignited inside the star, and then we have light. That's the moment when we have a birth of a new star, right?
Yes,
Okay, great.
good. So this is um, what we know about the start of the hydrogen burning. Okay. Now, remember the star is accreting and suddenly it has started burning hydrogen. It would release a lot of radiation pressure from the center or the core where it is burning hydrogen from.
Okay.
That radiation pressure will move outward from the core. I don't know if you have been in a nuclear plant, but the radiation produced in a nuclear plant is so much that nothing can come back inwards into the center of the fuel burning system. Okay, so the radiation pressure from this hydrogen burning process goes outward and blows away every other gas that could possibly fall into the forming star and stops the accretion process. Whatever mass the star has achieved when it starts burning hydrogen would now be the mass of that star, okay? Because it can no longer accrete any further.
Hmm. Okay.
Radiation pressure stops the entire process, blows away the gas, and leaves most of the dust particles remaining in the disk. It is most of these dust particles that eventually, after the star is formed, that go ahead to form the planets that move around the stars.
Okay.
This is the beautiful story of our understanding of low mass star formation, but the case is completely different. Well, what I just described now
Excuse me, James.
happens
James,
over,
I need a question here. So
yeah.
you are mentioning that the planets that form around the star originally come from inside the star.
So it is remember it has an accretion disk. When it rotates, it develops an accretion disk, okay? That helps it funnel material
Hmm.
into the central object. Now that disk is made up of gas and dust. When the radiation pressure starts, it blows away the gas fairly easily. Of course, maybe to further away in the disk, stops accretion, but the dust stays. So you will always see, we call it class 3 stars for low mass stars, where you have the central star that is shining and there is a ring of dust and gas around it
Okay.
that still keeps moving around. They no longer fall into the star. It's no longer possible. So they collide with each other and some of them combine and grow in mass until they become planets.
Oh, wow. Okay. So basically, we were born inside the sun.
Um, we are born at the outskirts of the sun.
Yeah.
The sun is here. It's a huge ring around the sun that is made up of small dust particles that combine to get bigger and swallow each other and get bigger and get bigger.
Hmm.
And then that's how the planet came up.
Okay. So my other question, you mentioned the aurora. Like, why do we have the aurora around the Earth while it should be around the star itself?
So we also have auroras around the star also. So that is a different discussion for another day, because the aurora is just charged particle plasma that connects to magnetic field.
Okay.
Okay. So if you have the surface of a star releasing what we call, well, the solar physicists call it coronal mass ejection,
Okay.
they release hot plasma from their surface, and this will travel in the direction where it is released, right? If it comes towards the Earth, Remember, this is a huge beam of plasma. The Earth in the North and South Pole has magnetic field, right? The
Yes.
origin and the closing loop of the magnetic field. The moment it hits that strong magnetic field area, it generates emission. That is actually just synchrotron radiation. Remember, if you connect electron falls into a loop of magnetic field, it releases synchrotron radiation, which is continuum. So that's how auroras are formed. We don't see auroras, for example, in Africa, because we are not very close to the poles where the magnetic field strength are stronger,
Yeah.
which is where the charges, of course, the moment you have charged particles falling into the magnetic field, you easily find a concentration in the poles.
Yeah, okay. So my other question here, like you mentioned, you are studying the stars through radiation. So when the
Yeah.
radiation hits your device, how do you decide whether this radiation comes from a rock, comes from a gas, comes from the inside of the star? How do you decide?
Okay. Would you give me option to share screen and show
Yes.
you?
Then you
Okay.
give me a second.
Let me try to find got a number of lecture notes. Okay, good. So the question about how we distinguish the source of the radiation is quite easy to understand. It comes from what the emission processes are. Okay.
Okay.
If you drive a car in a very hot day and the engine, of course, heats up the bonnet of your car, you can almost, if you look carefully, see radiation coming from the bonnet. It comes out like some transparent flame, okay? That is continuous thermal radiation. This can come as a result of heating. Okay. Now, we know if something comes from dust or come from gas, from the kind of radiation we pick up. If it comes from dust, it will be continuous. We have two kinds of radiation processes: continuous radiation, which will be broadband. It will cover a lot of bandwidth. Okay, it can go from one frequency all through to another frequency. And we have what we call the line radiation or line emission, which happens specifically at a given frequency, just one frequency. So for the continuous radiation, we know that if you observe, for example, a human body that is 37 Kelvin, you can produce this kind of thing that we call black body radiation. Okay?
Okay.
So if you want to observe a human body and you want to get the peak emission from our own bodies, which is similar to black body, the peak point is somewhere around 10 to the power 13 hertz. For the sun, it will peak at about 10 to the power 15 hertz. For a massive star that is 100,000 Kelvin in temperature, you would find the peak of its black body emission, continuous emission, at 10 to the power 16. And this is for cosmic microwave background. Okay, that
Okay.
usually would peak at 10 to the power 11. Now, this is how we studied the spectral index. Now, if I want to tell if an object is emitting like a black body, I just need to observe it at different frequencies, measure the brightness, okay, at different frequencies from radio, microwave, infrared, UV, and I just make this kind of plot. I can tell if it's a black body system. Now that's thermal. This is purely due to the heating, right? There is another form of thermal radiation. If you heat hydrogen high enough, you will break it up. So I just described one kind of continuum emission, and that is the thermal emission.
Okay.
And in the dust emission, which is also thermal as a result of the temperature of the body, there is another one that is also thermal. We call it Bremstalon emission, or we call it free emission. This is what is described here in this movie. And it happens as a result of heating again, because if you heat hydrogen high enough, you break it into positively charged ion and negatively charged ion. The negatively charged one is just electron, right? So this will coexist in an environment, but the electron being lighter will keep moving, right? So if the electron travels, as you can see this one, and comes close to a positively charged ion, then this attracts it and deflects the path of the travel. The same circumstance, so I understand completely.
Okay, we can go ahead.
Okay, so I've described the black body radiation, which is one kind of thermal radiation. The second one is the free radiation, which we also call the Bremsstrahlung radiation. And this is as a result of the deflection of a charged electron or charged particle, which is electron, when it is in the presence of the electric field of another charged, negatively charged particle. So this is a negatively charged one. The energy here, okay, on this
Okay.
part is different from the energy on this part when it's deflected. So the difference in the energy is released, is the energy released. This is also continuous. The third one, which is the one we just talked about briefly, is synchrotron radiation. This is mostly when you have relativistic electron coupling into magnetic field, and it gives out this radiation. It's not only the synchrotron one, we also have the cyclotron radiation, which is also continuous. So when we see this kind of thing, especially the thermal emission coming from dust, we can use it to trace the distribution of dust particles in a region. And that can
Okay.
tell us if there is concentration of dust particles, which means a core that will form a new star is now existing in that region. Okay,
Okay.
good. So if we find Bremsstrahlung emission, this is also interesting because you need a lot of heat to ionize hydrogen. So if we detect things like Bremsstrahlung emission, the information we get is that there is already high enough temperature to break up hydrogen to form electron and proton. Okay.
Okay.
So seeing free emission means a lot of things to us. It means a high density. It could mean a huge shock, because if you impact the gas so hard, you will break up the hydrogen in it.
Okay.
Okay, good. And if we see synchrotron radiation, we can use it to tell that magnetic field is also playing a role in the star forming region.
Yeah.
Good. So this is how we piece the information together. On how we know whether it's gas or not, when it is a gas or any other element, you can find, yeah, I'll try to be quick. I'm just answering your question. After
Okay.
doing that, I'll go into Highmass star formation. I think we should be done, so you can focus on taking care of the little girl.
Yes, we can
Okay.
continue to the next part.
Okay, good. So this part just tells you that it is coming from gas. Every molecule or atom of gas that we have in the universe, if you excite it with a certain energy, or if you change something about that molecule, it will radiate at a certain frequency or wavelength. The most abundant gas is neutral hydrogen in the universe. And we pick up neutral hydrogen emission or radiation at 21 centimeters. That is about 1.4 gigahertz. What we are simply picking up is something that is demonstrated in the first animation there, that you have a proton spinning in one direction, right? And electron spinning in the same direction. If for any reason you change the spin direction of the electron, then you release emission at 21 centimeters.
Okay.
So when we observe at 1.4 gigahertz and we find this nice spectra of hydrogen, this is the process we are picking up. And we can use it to tell how much hydrogen is distributed in a region. Remember, this is the most important gas in the formation of a star.
Okay, and
Because this
yeah,
is the real fuel. This is the hydrogen that it combines to form helium. Okay?
okay, yeah. Now you decided that every type of radiation is related to either a certain gas or a certain body. How did you do the experiments to decide that?
Okay, good. So I like the question. Permit me to use the web to just show you how we know where which radiation is coming from. NRA. Catalog, you can find different emissions. So in the laboratories, every molecule, okay, the chemist will excite. Remember, we have molecules that the atoms vibrate or rotate.
Okay.
So they excite it differently and they try to find at what wavelength this vibration will release radiation.
Okay.
So Jet Propulsion Laboratory, JPL, and a couple of laboratories come together and excite different molecules. I'm just going to show you an example of, let's say, 1.4 gigahertz. Okay, I can start with high frequency, let's say 220 megahertz. No, let me use gig to say 221 gigahertz. If you simply search, this is going to pop out all the molecules that are possible. Okay, you can detect nitric acid at 20.00001910.
Okay.
Okay, if you
Okay.
observe at this frequency and this gas exists there, if it does exist, you'll find it.
Uh-huh.
And you can see different molecules. Okay?
Okay. Yeah. Yeah. Got it.
And there are hundreds of these. Actually, just between 220 and 221 gigahertz, just 1 gigahertz width, there is 10,874 lines.
Okay. Yeah. Then that's the universe.
Yeah, so there is a lot of molecules, different complex molecules. Some of them, remember, this is something simulated in the chemistry lab, okay? So what happens is when we do observation and find some of the lines we don't know, we compare it with this and we say, okay, we discovered this. For example, Alma, where I worked a couple of years ago, discovered sugar in space. It's not the edible sugar, it's the poisonous one, but it's still sugar, it's glycerine or something, okay?
Okay. Yeah.
So that's how we make discoveries. Uh, all these molecules are listed here and the frequencies where you can find them. It doesn't mean we've seen them in the universe. They may be there somewhere. We just haven't found them, some of them, but many of them we already know.
Okay.
Okay, so this is how we know which molecule is coming
Yeah.
from where.
Okay.
Good, so I will go back to my slide. Not this one. Okay, so that is one kind of line emission, the hydrogen. Um, so many other molecules, as I showed you, carbon monoxide, carbon sulfide, carbon nitride, and so on, give out radiation. There is another special kind of radiation that comes from gas, and that is what we call the maser emissions. This is my favorite because it's what I used in most of my PhD studies. Masers are extremely bright. You have used a laser pointer before, right?
Okay.
Light amplification by stimulation of emission of radiation, right? That
Okay.
is for light. If you point it from here, it gets as far as the sky. You can even use it to show people night sky. Those are lasers. If you simply change the light component to microwave, then you get what I'm talking about. Okay. So lasers and masers are same, except that lasers is for light and masers is for microwave.
Okay.
Microwave is in the radio wavelength. So what happens is that naturally the electrons in a molecule prefer to stay at the lower energy level. That is the natural place. It's synonymous to humans. We always want to be in our comfort zone, relaxed and calm. But if you have to run from where you are to, say, the center of Cairo and run back to your home, you would have given a lot of kinetic energy to your system. Okay?
Okay.
Your body temperature will go up, but that is a higher energy level. That's not where the body wants to be. So the body wants to come back down to the original relaxed, calm environment or the calm energy level. So you will pant, breathe quick, you will sweat to give away some of the energies until after some time, you're back to your ground state, okay,
Mm-hmm.
and very relaxed. This is synonymous to what happens in masers. These molecules are there, right? But
Okay.
the dynamics, a lot of things are happening due to star formation. There is the rotation, there is the outflow, which I have mentioned to you. And this push against some of these materials or the molecules. There is the radiation coming from the center, right?
Okay.
And this also heats up some of these molecules. When you heat up the molecule, all you're doing is changing the location of the particles from one energy level to a higher energy level.
Mm-hmm.
When you do that, that is called pumping.
Okay.
You have pushed, remember, in a ground state, the normal situation is that the lower energy level should be more populated with the electrons. But when you push, when there's a process without radiation or collision, these electrons move to higher energy level. At that condition, that is called population inversion. The normal
Mm-hmm.
population is that higher population will be down, okay, and lower population electrons will be up. So if you carry out any process that inverts this population and makes the electron go to higher energy level, as you can see in the movie, more electrons in E2, which is higher than E1, then you've inverted the population. And if for any reason a seed electron, something stimulates the emission, stimulates this electron to come down back to a lower energy level. That is the stimulation part of the laser or maser, right? In this case,
Okay.
maser. Then the particles will release radiation and come down to lower energy level.
Mm-hmm.
This is maser. And this has nothing to do with thermal processes. It's maser emission, non-thermal.
Okay.
Okay, so this happens in molecules. We know about OH, which we call hydroxyl. We know about water masers, which are used a lot to measure distances to stars. We know about methanol, which is mostly in the rotating disk of forming stars. We know about silicon oxide, which are found in outflow shocks. Good, so that's my answer to your question. Okay, so I will try to now go to star formation. Um, I won't describe radio telescopes. Maybe we'll find some other time
Okay.
to do that, but just give me some time to.
Right, please.
So this will probably be the last slide I will show you about Highmass star formation. And this will highlight many of the radiations, well, a few of the radiations I have pointed out to you. I mentioned that in Highmass star formation, that we are aware that they start from giant molecular clouds. This is the cloud of gas and dust. The image here shows infrared observation, and the dark spots you see is just telling you that there is a lot of dust. Okay, and we call
Okay.
this dust extinction. Dust extinction is similar to what you see when you drive behind a car that is pumping out fumes. If a car is pumping out fumes and you're driving behind that car, you can't see what is beyond the fumes in front of you, right?
Sure.
Because this dark smoke absorbs all the light from the other side. So that's why we see these dark spots. These are where massive stars form. And we recently know that because in the giant cloud, there are clumps, okay? It's not a smooth density distribution, but it's a bit clumpy. Think about it as this sphere of gas, okay? The colors are not purely the same, which means that the column density is slightly different, variant in the cloud, okay? So we think from observation that some kind of collision between smaller scale clumps will form filaments like this. You see a smooth line of filaments due to collision of two clouds within the huge giant cloud. And fragmentation, the filaments will stay slightly unstable and fragment and form small cores, as you can see, bright spots within the long filament, okay? And these are the cores. These cores will achieve good enough condition to excite maser emissions. And remember, this is accreting more materials, so the density will increase, collision between particles inside will increase, and with more collision comes increase in temperature. So this becomes warm. The temperature around here is between 20 and 30 Kelvin, and these temperatures will start growing to up to 50, get up to 100 Kelvin and above. And we know that the more this temperature rises, the more you are the likelihood of breaking up the hydrogen to form positive charge, and the electrons will become higher. So you generate these free particles. And remember the deflection I told you about would start happening, and then you see free emission. This image here is actually centimeter emission, which is this free emission detected in forming stars. And these are the names of the stars.
Oh, yeah. Okay.
Good. And over time, because this density will keep rising, the free emission will keep increasing in size. You can have what we call extended H2 region. The neutral hydrogen we in astronomy we call H1. The ionized hydrogen we call H2. So if you hear me say H2 region, I just mean ionized hydrogen cloud.
Okay.
So the ionization will continue. If it starts, it's usually very small. Okay. If it goes ahead, it gets bigger and bigger as you ionize more and more of the hydrogen. Okay, so remember that these cores are rotating. Okay, I mentioned the angular momentum, and they would release outflows. I didn't show the outflow here. I showed only one, but you can see where I mentioned that you have high velocity jets and you have low velocity outflows.
Okay.
The two of them are illustrated in this blue image. How we know about the velocity of the outflowing gas is that we observe the source multiple times, and we look at how the position of, for example, masers are changing, okay, in multiple observations. And then we can calculate the motion in the direction it is moving, right? So in this case, the radio continuum, this is free emission, okay, due to the shock from ejected material that will ionize the environment as it travels outward from the object.
Okay.
So that is a jet, and this can be terribly fast. In this case, this jet is 500 kilometers per second. Every second, the ejected material travels 500 kilometers.
Okay.
Now, the water masers are represented with these crosses that you can see. And this was observed in multiple epochs, and their motion is recorded for this group, 13 kilometers per second, for this 18 kilometers per second. For this guy, arrow 7, it's actually 70 kilometers per second, which is more than 4 times the other ones. The reason being that this maser was excited closer to the part of the jet that is traveling very fast. Think about it. If you stand close to a train, okay, you will feel the push from the air that it blows at you more the closer you get to the train.
Sure.
So these jets are moving so fast, and any maser excited close to its path will have higher velocities. Just simple. Okay, the ones further away from the path had lower velocities. And if you calculate this motion, you can generate this huge wide angle outflow. Probably some of it excited by the jet, some of it excited by the low velocity outflow. Okay, the entire story I've told you will be illustrated in this simulation. So we start from giant molecular cloud, which is here, and oops. Okay, over time, the cloud will collide. You start seeing filaments. Okay, you see beautiful lines of filamentary structures, which is similar to this. We will zoom into one of the filaments to see how fragmentation happens. Okay.
Okay.
The next step is to fragment. Okay, that is one filament. You can look at it in all direction. You see nice long filament. See this?
Okay.
Now, the angular momentum, you can see the rotation. So as it rotates and fragments, you can see small white cores, okay, fall out from it. Those are the dense cores. Okay, they are these ones. And they will continue rotating and moving, okay? And accreting. As they rotate, they accrete more materials around them. Okay. So if they accrete more materials, they get to hot core, they drive outflow, they ionize their environment and form H2 region. They continue, while they are ionizing its environment, they also continue to accrete. We don't know how to explain this in massive stars. And then they get old and they explode. You already heard about supernova explosions. They explode into a supernova, and that is the end of their life. And this whole thing happened in just about a few million years. It's long in human perspective, but in understanding massive stars, that is very, very fast. Okay, I'll stop there. Otherwise, I'll take so much of your time. And
yeah, that has been really, really amazing and really, really universal. I don't know what to say. I really enjoyed it. Thank you, James, for that so much indeed.
no, thanks a lot.